And that would be okay. Again, it's implied that you start at 1 and end at 5. With me? Okay, what if I want to do a different sequence, but I'd like to do infinite? So what about 1, 4, 9, 16, ... forever? So then I could write a sub n equals n squared. That's the preferred one, right? That's the one we like. If I don't put any restrictions, that means it goes forever. How do you think I could write it using this notation? N squared, like this. If you don't put anything on it, it goes to infinity. All right? It's implied again. Starts at 1, never stops. But if you really want to be clear about what's happening, you can put n, not n equals infinity, because it can't. You just put infinity up there. And that would mean it's going to go to infinity. You could even put n equals 1 down here and then infinity up there. Those are not used as commonly in this class, these notations. But if you see them, I don't want you to like freak out. All right. I think we're ready. No, one more. Let me just adapt this a little bit. What if I wanted 9, 16, 25, 36, forever, ... So I heard this one. The one with the brace, you could go n squared and then n equals 3 down here. Do you all agree with that? I didn't do the one that we prefer intentionally. Because here's what I want. I want somebody to give me the formula that would generate this sequence, but you have to start at n equals 1. I'm not going to allow you to start at 3. So that means when you plug in 1, it needs to spit out 9. And then when you plug in 2, it needs to spit out 16. And when you plug in 3, it needs to spit out 25. N plus 2, the quantity squared. Do you agree? All right, so if I start at 1, 1 plus 2 is 3, 3 squared is 9. Then I go to 2, 2 plus 2 is 4, squared is 16. That will do it, right? Good, this is good. All right, now we're going to have some fun. I mean, I know we're already having fun. It's going to be even more fun. I'm going to start putting sequences up on the board, and I'm going to ask that you raise your hand. I don't want anyone shouting out, not as if this class shouts out, but I want you to raise your hand if you can come up with the formula, and we're going to see if you can generate the formulas for the sequences I give you. And this is a point in the class where we start to kind of see, like, you know, where people's brains are as far as can you see this or not, you know? And it's for some people it's really easy, for other people it can be really tough. So first example of this I'm going to give you the easiest one first. So one person at a time, please raise your hand. Who wants that one? I want the formula a sub n, and I'm forcing you to start at 1. Anyone? Anyone? Oh yeah, let me say one more thing. If you raise your hand and answer, then you're out for the day. You can't answer another one. Okay? So, yes? N? Yes? N? Everyone agree? Sorry if you had yours up first. I'll give you a chance at the next one. A sub n is n. Okay, so a sub n is n. All that does is generates the natural numbers, right? It just spits out 1, 2, 3, 4, 5. Great. Okay, let's do another one. Okay, who wants that one? Okay, what do you got? N plus 4. Everybody agree? Okay. Good. Who wants that one? What do all of these sequences have in common? They keep on going up by 1, up by 1, up by 1, up by 1. The difference is where they start, right? The first one starts at 1, the second one starts at 5, the third one starts at -7. So how are you going to get to -7? So who has it? What do you got? N minus 8.
So I can't go anymore.
Hmm?
I can't go anymore.
Not right now. Just wait. Questions? I'll put a star next to this one. This one's going to come up quite a bit. So who wants that one? 2n. 2n. Those are the even numbers, aren't they? That's going to generate an even sequence starting at 2. These braces get real sloppy with me here, sorry. Who wants this one? Laura, you're out. I know. I'm going to wait till I give you harder ones. Because I know you'll want to answer the harder ones when I put them up there. Unless nobody has it. Go ahead. 2n minus 2. So here's kind of the way you can look at this. If you understand that 2n generates the even number starting at 2, these are all even numbers. All you've done is shifted this 2 back to 0, this 4 back to 2, this 6 back to 4, this 8 back to 6. So all you've done is subtracted 2 from each of these, right? So that works. How about that one? Remember the good old days when I used to call on you? Let's see here. Albino's up. Where are you? 2n minus 14. What do y'all think? Agree? Yeah? Same idea. 2n generates the evens, but you're going to shift it. You're going to shift from 2 all the way back to 12, so you have to take 14 away to do that. All right, now, next one is a little different. I'm going to call on, let's see, Laura. Laura, can you generate the odd numbers? So starting with 1, can you generate the odds? So I'm asking for the formula that will generate the odds, starting with 1. Let's give Laura time. Is he right? What is it? 2n minus 1. Wait a minute. 2n, I thought that generated the evens. It does, right? But what does subtracting 1 from each even do? Give you the odd right before it, right? So you're basically taking this list right here, and you're taking 1 away from each one, and that'll create 1, 3, 5, 7, 9 instead, right? Good? How about, let's start it out at 13, 15, 17. Who wants that one? Go ahead.
2n plus 11.
2n plus 11. What do y'all think? Plug in 1, what do you get? 13? 2, 4, 11, 15, right? So this concept of 2n is really important. 2n plus or minus an even number is going to create even numbers. 2n plus or minus an odd number is going to create a list of odds, right? Good, good, good. Let's throw a wrinkle in this now. That's not fair of me, Laura, to put you on the spot like that. No one ever said I was fair, though. Anyone here? Do the fractions freak you out? No? Nobody? Let me give you a hint and then let you think about it some more. Look at the numerator completely separate from the denominator. What is the numerator? Those are just odd numbers, right? And the denominators are just even numbers. So it's like, can you generate a list 7, 9, 11, 13? I heard 2n plus 5. Does that create the list 7, 9, 11, 13? Okay. Now generate the list on the bottom, 4, 6, 8, 10. 2n plus 2. And no, the 2n's don't cancel, right? You can't do that. And that's it, right? That'll do it. Now, here's something that's tricky about a problem like this. I gave this to you completely unreduced. So let's reduce, well, there's only one fraction that reduces, but let's reduce it and let's see what we would have had here. Let me go one more fraction out, which would have been 15. No, that's still wouldn't have reduced. So, see, if we would have reduced this fraction, then that might have thrown you off, right? Do you agree with that? So you have to be careful. You need to be able to go back sometimes and rewrite the fraction to pick up on the pattern. It does, yeah, but who cares? Yeah, it did. I was going to go the next one out, but I said it doesn't reduce. It obviously does, 15 over 12. Close, 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 close. 3 to the n is the, it's almost there. The problem is if I plug in 1, minus 1, very good. 3 to the n minus 1. So let's see where this comes from. First of all, you recognize that all of these are powers of 3, right? You probably recognize that 3 is 3 to the first, 9 is 3 squared, 27 is 3 cubed, and then it would go on. The only thing really was, what about this first one? 1. That's 3 to the 0. So what do these all have in common? Base 3, right? So I know that's never going to change. All I need to do is generate the powers. And aren't the powers just the natural numbers, but starting at 0? So you can create the list 1, 2, 3, 4, 5, 6, right? But to create the list 0, 1, 2, 3, 4, 5, 6, you have to subtract 1. Do y'all see it? I'm sorry?
When you write it like that.
When I write it like that, what?
Yeah, when you break it down.
Oh, when I break down. So you need to, yeah, be ready to do this. This is going to be part of the fun we're having in here. All right. I'm going to move on. negative 1, 1, negative 1, 1, negative 1, 1. Well, yes. Negative 1 to the power n. All right, so I'll open it up to everyone again if you want to answer. Okay. Negative 1 to the n. Do you all agree? Yes, this actually works. Because if n is 1, we get negative 1 to the first power, that's negative 1. If n is 2, negative 1 squared is positive 1. And then it's going to just keep switching back and forth. This is known as an alternating sequence. Alternating sequence. Can somebody else give me a formula that would do the same exact thing? N here, but not plus 1. What about plus 2? What would happen here? If I plug in 1, what do I get? I get negative 1 cubed. What's negative 1 cubed? Negative 1. If I plug in 2, what happens? 2 plus 2 is 4. So I get negative 1 to the 4. That's going to be positive 1. So that's going to do the same thing, isn't it? In fact, I could do n plus 4, and that would do the same thing. Wouldn't it? As long as it's negative 1 in the parentheses, and as long as this is an even number out here. 0, this is really like n plus 0, right? So 0, 2, 4, 6, those are all even numbers. That should generate that sequence. All right, let's try something else. What if I want an alternating sequence again, but this time starting with positive 1 instead of negative 1? Negative 1 to the n plus 1, or n plus 3, or n plus 5, or n plus 7. Know those two. We're going to use these a lot. Okay. How about negative 3 halves, 5 fourths, negative 7 eighths, 9 16ths,